Hello everyone. In this video, we are just going to get a deeper understanding of internals of real-time operating systems. Let's get started. So this is the program that we wrote in the previous video in which we just understood what is a blocking code format or a method. And in this video, we are just going to understand how a basic real-time operating system switches from one thread to other thread, or let's take it in this way. Till now we did not understood what are threads, but we are just going to understand how an real-time operating system switches from one function to other, even though we are having infinite loop in each of the function, and help us to achieve parallel executions simultaneously. So let's get in detail about that. For that, let's alter this program a bit for understanding that internals of real-time operating systems. And what I'm going to do right over here is I'm just going to reduce the delay inside this light on, and again here I'm just going to give the delay of 2 seconds inside each of the light on and light off function, and here I'm just going to empty this main function infinite loop, and instead of that I'm just going to add infinite loop inside both of these functions, light on and light off. So I'm just adding while of 1, and inside the while of 1 I'm just going to add each and every content of the light on and light off function. And here I'm just going to call light on and light off function. Before that, care of, let's take it to be global variable equal to 0, and if the global variable equal to 1, I will just call this light on function, else I will just call this light off function. Remember that we are not going to get into the infinite loop of the main function. Instead, before that itself we are just going to call these two functions. Let's demonstrate this program. Since we are having UART transfer function, we can demonstrate these functions with the help of Docklite serial terminal software or any other serial terminal software. Now let us try to switch to the debug view of this cube IDE for understanding this program. I'm just going to right click on this project and click on debug as STM32 C++ application to move to the debug view of this environment or IDE. Switch. So whenever you do this, the program will be also dumped into the microcontroller. I have already connected the nuclear development board. Now I will just try to run this program and test it in the serial terminal. You can see the lights off is being printed for every 2 seconds, which means the program is stuck inside the light off function infinite loop, because the variable value is 0 right over here and the else part is executed and the processor is held inside the light off infinite loop, that is this one. And the important windows that you want right over here for understanding the internals is the registers window, which will show up all the register values, that is the basic register values, general purpose registers from R0 to R12, and special function registers like linker register, stack pointer, program counter and program status registers. Don't worry, we are just going to see each register in detail in a while. and then we need the disassembly window. So this is actually the conversion of this particular C program that we have written into assembly format directly. And in addition to that, we want this memory browser. If you don't have all these windows, just click on the window tab, show view, and select the respective windows that you want right over here. Now we just understood that the program is stuck inside the lights off, and now let us try to understand what happens internally inside the processor registers whenever SysTick interrupt handler interrupts the processor. So for that, the program is running still. Now I am just going to place the breakpoint right over here inside the SysTick handler. So the processor is paused right over here. So what is happening right over here is the program is being executing the light off, or the processor is being executing the main function light off from the main function right over here. And whenever the load value reaches the exact value in the SysTick handler, the SysTick peripheral actually interrupts the processor with an interrupt subroutine or interrupt service routine. That is this particular interrupt function, and the processor actually pauses all the operation it was doing right over here in main function, and it will come to this interrupt handler or interrupt subroutine function for executing all the lines that is available inside this function. Once on completing all the stuffs that is available right over here, or all the lines that is available right over here, the processor will be coming back to the main function, and it will resume back the same operation that it was doing before the interrupt function call or the subroutine function call. So how does the processor does this? Or in other words, we can ask like, how does the processor actually remembers all the things that it was doing before the interruption or before the interrupt service routine call? This particular register or the special function register stack pointer is useful for storing the address of top of the stack in the RAM memory location. Let me just open that memory in the memory browser 0x2001FFA4. I have opened that particular stack top memory location in the RAM of the microcontroller, and this linker register is the register which stores the address of the subroutine from which the processor returns, and the program counter register is also a special purpose register which stores the address of next instruction which needs to be executed in the program. And this program status register is also a special purpose register, and R0 to R12 or general purpose register, which is useful for all the algorithmic operations or arithmetic operations performed inside the processor. Any operations that can be done inside the processor can be utilizing these R0 to R12, but these registers are special purpose registers. So whenever, as I said, when the SysTick handler interrupts the processor will actually load the value of R0, R1, R2, R3, R12, linker register, program counter, and program status registers. All these 8 registers contents will be copied to the stack area in the RAM before entering into the SysTick handler. And upon completion of this particular SysTick handler, the processor will again restore back the copied data from the stack RAM location to the respective registers again, and it will resume back the process. This is how the processor does it. That is, you can clearly see I have just stopped the execution of the processor before the first line of the SysTick handler. So what the processor would have done is, as I said, it would have copied the 8 register values highlighted in the left: R0, R1, R2, R3, R12, LR, PC, PSR to the stacked memory location inside the RAM. So you can see clearly, leave this first top of stack address location. This is the R0 value which is copied. This is the R1 value which is copied. This is the R2 value which is copied. This is the R3 value which is copied. This is the R12 value which is copied. And coming to the main part, that is linker register and program counter. As I mentioned, all these registers R0 to R12 are general purpose registers, so they can be used for anything. But all these stack pointer, linker register, program counter and program status registers are special purpose registers which are meant for a particular purpose. And just try to understand why this program counter value is different here. That is, we have 2C0, 8000 2C0 right over here, and here we have 8000 260. Why it is different? Let's try to understand. Before, this copying of content was done when the processor was executing the main function, but here the program is halted after entering the sysdig handler. So here the next instruction which needs to be executed by the processor should have been in the location 8000 2C0 as per the content right over here. So here also the program counter serves the same purpose even inside the sysdig handler. But at the time of copying from the main function, the next instruction which was to be executed from the main function before the interrupt or the sysdig handler interrupted the processor would have been in the address of 08000 260. So that is why we have a mismatch of program counter value, linker register value right over here. So this value stored in the stack would have been the address of the next instruction to be executed in the main function, and this value right over here is the address of the next instruction to be executed currently inside the sysdig handler. I am just going to click on the step return for returning from the sysdig handler so that we can visualize the same content, that is 8000 260 value in the program counter. You can see it has returned. So now I hope you understood how a program counter register functions. It is the register which holds the address of the next instruction which needs to be executed in the program. And what if we can use this particular program counter register for changing the sequence of operation of the program? And as we know, this program that we have written is executing, or the processor is stuck in this program inside the light off function infinite loop. I am just going to run this program again. It is running continuously, and now what I will do is I will just place a breakpoint inside the sysdig handler again. Now the program is halted or stopped, and we very well know the light off is the function which is being executed. Now I will just try to manually switch the content from light off thread to light on thread using the manipulation of program counter stack area data. So now the program or the processor is stuck inside the sysdig handler, which means the processor would have stored the program counter data in the main function inside the stack area. Now the stack pointer data or the stack address is 2001 FFAC, which is open right over here. Now I am just going to manipulate the program counter data with the lights on function. So this is R0, R1, R2, R3, R12 linker register. This one is the program counter. I am altering this with the lights on. You can see lights on addresses 00045C. Now I am just going to remove the breakpoint and I am going to run the program. This time when I run it, you can see the light on thread is running. Now we successfully switched manually from one thread to other. This is how RTOS actually operates with the internals of the processor, ARM Cortex-M processor, for switching from one thread to other, so that sequentially all the processes runs in a periodic or in a certain algorithmic fashion. Based on the RTOS algorithm, this is done. And I hope in this video you understood how internals of processors are handled by the RTOS, and you learned how to manually switch from one thread to other, even though we have infinite loops in each of the thread in the program. See you in the next video. Thanks for watching.